So now we're going to dive into the material that was set aside for today, Tuesday, the 28th, as opposed to what we were doing on last Thursday. And the good news about today's material is that there is very little math involved. There's no on the board or on the document camera examples. We're going to be talking more about the process of sampling. So hopefully this will be a little break for your math brains and nice change of pace from the last kind of more intensive days we've had. All right, so as a reminder, we have two types of statistics that we can be interested in. And I mentioned these two types of statistics a couple classes ago, but here they are again. Descriptive statistics are what we did in the first third of the class, so that very first unit, where we were looking at data from a sample and describing it. I'm just saying this is a mean or a typical value, this is what it looks like in a frequency distribution, this is what it looks like in a graph. Just taking data and describing it. With inferential statistics, which we're working towards with all this probability stuff, and which we'll be doing for most of the rest of the class, we'll be using a sample to make a generalization about a population. What that means is that we're going to take a sample and we're going to use that to learn about a population more broadly. So imagine you wanted to know, what people in the United States think about the death penalty. It's going to take you a really long time to ask every one of the 300 million people living in the United States what they might think of the death penalty. A lot of time, a lot of money, chances are you're just not going to get it done. But you could take a sample from that population, figure out what attitudes look like in the sample, and use that sample to learn something about the broader population. And when we do this, we say that we are making a generalization. We're taking a specific sample, and we're using that to make an assumption or a generalization about what's going on in that bigger population. And a key here in this definition that I've put up this time is this term representative sample. Because as we'll talk about, some samples are better than others. Some samples will allow you to learn about a broader population, while some will completely mislead you. So in this class, we're going to talk about representative samples, where they come from, and why they are going to be useful to us as we move into this unit of inferential statistics. Briefly also, there are two types of inferential statistics. The one that we're going to be working toward in the remainder of this unit will be something called a confidence interval, and that'll let us estimate population values. So if we were thinking about death penalty support, you could come up with a range of numbers that would tell you it's most likely that, between this percentage and this percentage of people in the United States support the death penalty. With hypothesis tests, which will be what we do for the final third of the class in the next unit, we'll be testing statements about what might be true or might not be true in the population. So we could test a statement like, how likely is it that it's the case that 50% of the people in the United States support the death penalty? We can put a pin in these for now. These are just examples of the types of inferential statistics we're going to be doing later on. And for the remainder of this lecture, I'm just going to talk about sampling. So how do we get a sample that's going to allow us to calculate these kinds of statistics and answer these kinds of questions? And our main answer is that we want a representative sample. The absolute best kind of sample, and the sample that will always give you a representative sample, is something called a simple random sample. It's considered the gold standard of sampling. If a sample is a simple random sample, you know it's going to be good every single time. And when you do research design and research methods classes, they'll talk a lot more about different kinds of samples and so on. But for our purposes, we'll just say that this is the best kind of sample that you can do, and we're going to talk about why that is and what it will do for us in statistics. And in a simple random sample, every member of a population has an equal chance of being selected into the sample. So this means that every single member of whatever population you're interested in has an equal chance of ending up in the sample. And there are two steps required for this to happen. One is that you need to list out every member of a population. The second step is that you need to use some sort of random process to select members of that population from a list. So if I were to take everybody's name in the class and write it down on a piece of paper, put all those pieces of paper in a hat, and then, stick my hand in the hat and pull something out, that would be a simple random sample, and then pull out 5 names until I had a sample of 5 people. That would be a simple random sample of students in this class, because I would have gone through those 2 steps. I would have listed every member of the population, where we're going to say the population is the class, and then I would have used some random process to select members of that population into my sample, where my random process would have been feeling around in my hat full of paper and pulling something out. And if I did that 5 different times and got 5 different names, I would have a simple random sample, because everybody would have had an equal chance of being selected into that sample. Other examples of simple random samples in the real world are things like jury selection. So juries are often selected from a random sample of registered voters, where the population of interest is registered voters, and the random sample is done through a computer just making random selections of names off that list. Powerball Lotto, another example of a simple random sample. So they've got that big ball full of balls that turns around and turns all the balls around, and then spits out a random sample of numbered balls. And this is a simple random sample where your population is the total set of balls in your big ball of balls, and the random sample are the 6 balls that actually get spit out to come up with that lotto number. Another example of a simple random sample would be one you guys are familiar with already, which would be picking M&Ms out of a pile of M&Ms. So when we did that in class, we could have said that our population was a bag full of M&Ms. So your total population, the total set of things you're interested in, were those 14 or 15 M&Ms that you had in your bag. And when you picked out M&Ms and recorded colors of different M&Ms, you could have created a sample out of that population. Or if you picked out, say, 3 M&Ms out of your bag, recorded the color for each one, you'd be creating a sample of M&Ms using simple random sampling, where you have all possible M&Ms there. Each one had an equal chance of being selected when you picked it out of the bag, and then you were recording those outcomes. For the purposes of this class, we will assume that all samples we see are simple random samples. In reality, simple random samples are often difficult to pull off. So imagine you're actually trying to understand death penalty attitudes in the United States. You can't actually get a list of every single person who lives in the United States in order to sample them. There are lists that include the vast majority of people, so lists of addresses or lists of phone numbers, but then people who do not have an address or who do not have a phone end up not being counted. And then practically also, even if you had a list of everybody, the chances that every person you contact to try to select into the sample, that they're going to want to participate and be in the study, that also tends to knock people off. So most samples that you actually see out there in the real world use other forms of sampling to come up with samples. But for this class, we're going to assume that all samples operate like this, where they follow this simple random sampling process that gives us these really good, really strong representative samples, where I'll talk about what representative means on the next slide. But just as a heads up, we're going to treat samples that are not actually simple random samples as random samples in this class. All right, so I keep using this word representative, and I said inferential statistics use representative samples. And I said that simple random samples create samples that are representative. So what does that actually mean? And a representative sample is a sample in which the characteristics of the sample can be expected to match the characteristics of the population. So whatever, if you have a numerical variable, whatever your population mean is, you'd expect your sample to have the same mean. If we're thinking in terms of percentages, whatever percentage of the population supports the death penalty, if you take a simple random sample of that population, you'd expect to find the same percentage of people supporting the death penalty in your sample. And you could do this for any statistic you could calculate. So if you created a frequency distribution of your population values, you'd expect to have a similar frequency distribution in your sample. Mean, median, mode, standard deviation, anything you could calculate for a population, you'd expect to find the same numbers in your sample. And so when we say it's representative, we mean that, in general, the sample characteristics are going to be the same as the population characteristics. And the only differences we should see between our sample and our population would be due to random chance. So anytime you're dealing with probability, so anytime you're pulling M&Ms out of a bag, or selecting names out of a hat, or Powerball balls out of a big ball thing, there's going to be some random chance involved. So your sample statistics are often going to not match your population parameters exactly because of that random chance. But aside from some random variation that's not really going to pull us in any particular direction, it's just going to be totally random noise, aside from that noise, we're going to expect our sample statistics to match our population parameters. And this lets us use representative samples for a lot of things. And a real-life example of how this works and how this is used is one that we see very often, especially every time election seasons roll around, and that's in political polls. And what political polls do is they collect data from representative samples of typically about 1,000 voters per poll. And they ask those 1,000 people who are representative sample who they're going to vote for. Because the sample is representative, in other words, because the statistics of the sample are expected to match the population parameters, we can expect that whatever percentage of people say they're going to support candidate A in our sample is also going to match the percentage of people who support candidate A in the population. Whatever percentage of people in our sample support candidate B, we'd expect that to match the proportion of people who are going to support candidate B in the population overall. And again, this is this idea that a representative sample is going to have the same characteristics as the population that it came from. The only differences we should expect to see between the characteristics of our sample and the characteristics of our population will be due to random chance. And if you're looking at the results from political polls, you'll often see a statement about something called margin of error, where the margin of error tells you how much noise we expect to see in our sample. In other words, how far off, due to random chance, are our estimates likely to be? And so, again, a representative sample is a sample that is expected to match the population on any statistics you could calculate for the sample or for the population. And so it's going to be more or less the same, with the only exception being that random chance is involved. So in your sample of 1,000 voters, it might be that you just so happen to include more people in your sample who support candidate A than candidate B, just because of complete random chance. They're the people you happen to end up with on your list of people to include in the sample. And so there might be that random element, because when you're picking things randomly, you never know the exact set of outcomes. But aside from that sort of random noise, where maybe you'll end up with a little more support for candidate A or a little more support for candidate B just by chance, within some margin of error, we're going to be able to be pretty confident that our sample characteristics match our population parameters. And what we'll do later on in this unit is we'll talk about how we can actually calculate that margin of error and come up with estimates based on samples that are that we can be pretty confident in and really account for that. But before we get there, today we're just going to talk more about sampling and a little bit more about how it works and why it works. So how does that work? How is it that you can take a simple random sample from a population and come up with a sample that is representative of that population, every time, except for whatever bit of noise we get just from that randomness? And it works because it's based on probability. And it's based on aspects of probability that you guys have already seen in action. So what population parameters do is they provide us with a probability distribution. If 60% of people in the United States as a whole support the death penalty, then if you were to select any one random person out of the United States population, there would be a 60% chance they're going to support the death penalty and a 40% chance they're going to not support the death penalty. If you have a bag full of M&Ms, or a giant jar full of M&Ms, and that giant jar full of M&Ms is 20% blue, there's going to be a 20% chance that any single M&M you pick is going to be blue. And so whatever your population is, where a population is just some set of things that you're interested in, or people you're interested in, whatever the makeup of that population is going to determine the probabilities of the characteristics of any single member that you pull out of it. So again, if you have a giant jar of M&Ms, and here let's imagine a really, really giant jar of M&Ms where 20% of those M&Ms are blue, you're going to have a 20% chance of picking a blue M&M. 60% of the people in the United States support the death penalty. You're going to have a 60% chance of picking a single person who supports the death penalty. So whatever your population looks like can also be treated as a probability distribution. And we talked about this a little bit as well when we introduced probability distributions, and we said these can be based on population values. So we're back to that idea, and this is how it works. If your giant jar of M&Ms is 20% blue, you've got a 20% chance of picking a blue M&M. A probability distribution also tells you what to expect when you repeat some process that generates an outcome many, many times and record many, many outcomes. So this was one of our definitions of probability, which said that if you flip a coin 100 times, you'd expect 50 of those outcomes to be heads. So 50 out of 100 should be heads because you've got a 50% chance of getting heads. We can also think about this in terms of our giant jar of M&Ms. So let's say we've got our really, really, really giant jar of M&Ms, and 20% of those M&Ms are blue. If you were to pick out an M&M 100 times and record the color each time, you'd expect 20 out of those 100 outcomes to be blue. So for each one, you have a 20% chance it's blue. And we can also interpret this based on our definitions of probability as saying that if we were to repeat this process 100 times, we would expect 20% of our outcomes to be blue. So 20 out of those 100 M&Ms should come up blue if you have a 20% chance of picking a blue M&M each time. So these are concepts that we encountered when we first started talking about probability. And a sample is made up of many recorded outcomes. So this is what ties us all together and what brings us to our representative simple random sample. When you're taking a simple random sample, you're repeating some process many times. You're picking M&Ms out of the jar many times and recording outcomes. You're picking people out of the United States population many times and recording some outcome for each person, say support or oppose the death penalty. And if you pick 100 M&Ms out of your giant jar full of M&Ms, you can say that what you've done is you've taken a sample of 100 M&Ms. So you've used some random process to select 100 members of your population and recorded those outcomes. Based on that second bullet point there, which is that your probability distribution tells you what to expect when you record many outcomes, we can also say that those 100 M&Ms we picked, since we had expected 20% of them to be blue, if we think of those 100 M&Ms as our sample, we would expect 20% of our sample to be blue. So in other words, by using a random process to select outcomes, we can expect the sample statistics to match the population parameters. Because each time you select one member into your sample, you've got a chance of getting in the sample that corresponds to how common it is in the population. And if you record outcomes many times, you'd expect that chance to be reflected in the percentage of outcomes that have that characteristic. So each time you take a simple random sample, you're recording many outcomes, and you're going to expect to see those probabilities that you see in your sample match the probabilities in your population. And if this sounds familiar, you guys can think about the coin toss activity that we did a week or two ago, where when you tossed a whole bunch of coins and recorded outcomes and recorded different numbers of outcomes, you saw that the outcomes you recorded started to resemble the probability distribution that we started with. And we thought about each of your group's set of outcomes as being a sample of 10 different outcomes. When we combined it for 15 groups in class, we had a sample of 150 different outcomes. And what we saw was that each of our samples and our overall class sample of outcomes started to resemble that probability distribution that we started with. So this is that same principle of probability. We're now just saying that when we record all those outcomes, what we're doing is taking a sample. So sampling refers to this process of recording many different outcomes of some probabilistic process, and then treating that set of outcomes as the data you can actually see. All right, one more concept to go along with this. I said earlier that you can expect your sample characteristics to match your population characteristics aside from this random noise that comes from this being a probabilistic process. So if you pick 100 M&Ms out of a jar, you expect 20% of them to be blue, but it could be that really 22% of them are going to be blue, or 18%, or 17%, or even 30%, because you could just happen to pick more blue M&Ms or happen to pick less M&Ms just by chance. And you guys all saw that when we did the coin toss thing as well, where some people had distributions that looked really similar to the probability distribution we started with, while some people's were more different, and that's all just random chance. We can describe this random chance using this term sampling error. And what sampling error refers to is just the idea that random chance creates differences between samples and populations, even for your best representative samples. So your gold standard, simple random samples that are gonna, generally give you a sample that matches a population. We're still gonna see some differences between the sample values and the population values just because of random chance. And we call that sampling error. And this is why even the best estimates, even the best polls, have a margin of error, because you can never expect your sample to match your population exactly. You have to take into account the fact that once you start recording outcomes, you're dealing with probability, so things could always happen that are unlikely. And sampling error has a general tendency that we've also seen in this class in the coin toss activity. And a characteristic of sampling error is that smaller samples tend to have more sampling error. So if you take a smaller sample, a few unlikely things can really throw it off. So imagine that we're still pulling M&Ms out of that giant jar of M&Ms, and we're still expecting 20% of our M&Ms to be blue. So if we pulled 10 M&Ms out of the jar, we'd expect 2 blue M&Ms. 2 out of 10 is 20%, so you'd expect your sample of 10 M&Ms to have the same percent blue M&Ms as your giant jar. So you'd expect 2 out of 10 to be blue. But you shouldn't be surprised if you actually pull out 10 M&Ms and 3 of them are blue. Right, it's pretty close, but you just so happen to get one unexpectedly blue M&M. So random chance meant that you just so happened to get one extra blue M&M compared to what you were expecting. So that's a small sample, where we can easily go from 20% to 30% blue M&Ms by getting one unexpected outcome. But the larger your sample, the smaller your sampling error is likely to be. Because for your sample to be really different from your population, you have to have a whole bunch of unexpected or unlikely outcomes all happen, in that same sampling process. So imagine you pick out 10,000 M&Ms out of your jar. This is a really big jar. This is like a jar the size of a car. It just plopped on your front lawn. You don't know why it's there, but it's full of M&Ms, and you get to use it to explore the joys of sampling. So we're going to say now we're going to pick out 10,000 M&Ms out of that jar. If 20% of our M&Ms are blue in the jar, we would expect to get 2,000 blue M&Ms in our sample. So 2,000 out of 10,000 is 20%, so we would expect 2,000 of our M&Ms to be blue if we were to pull out 10,000 M&Ms out of this jar, where 20% of all the M&Ms in the jar are blue. So we would expect our sample characteristics to match our population characteristics. We would expect our sample to have 20% blue M&Ms because our population had 20% blue M&Ms. And if this happened, you should be surprised if you got 3,000 blue M&Ms instead. So if you got 30% blue M&Ms in your sample, 3,000 out of 10,000, that would be a really, really surprising outcome. Why? Because you would have to get 1,000 unexpected blue M&Ms. So to go from 20% to 30% blue M&Ms in our sample of 10 M&Ms, we only had to get one extra blue M&M. To go from 20% blue M&Ms to 30% blue M&Ms in our large sample, we had to get 1,000 extra blue M&Ms. And so we had to have 1,000 unexpected outcomes to get a sample that is as different as 20% and 30% when we had a sample of 10,000 M&Ms, as opposed to that one extra M&M we needed to get a sample characteristic as different as 20% and 30% when we had a small sample. And the main idea here is that the bigger your sample is, the more times you're recording outcomes, the more likely it is that unexpected things are going to kind of even out over time. And if you happen to pick some extra blue M&Ms on a couple rounds, you're also likely to encounter some rounds where you happen to pick M&Ms that are not blue. But when you have a small sample, a couple of unexpected outcomes can really throw things off. But large samples will tend to resemble the population more and more and more on average. And big deviations from what you'd expect become less and less likely and more surprising. So that's sampling error. Random chance creates differences between populations and samples, and sampling error is larger if you have a small sample because a couple of unlikely outcomes will throw everything off, and sampling error is smaller if you have a really large sample because a couple of unlikely outcomes just are not going to change much. You have to have a whole lot of really unlikely outcomes to throw everything off. Something to be on the lookout for in the world and in general when thinking about sampling are non-representative samples. So as I've talked about over the last several minutes, representative sample will always match the population. So the values of a representative sample, whatever statistics they are, you can expect them to match the same values in the population. So the mean should be the same, standard deviation should be the same, percentages and proportions should be the same. But if you have a non-representative sample, there is no guarantee that that's going to be the case, no matter how big your sample is. And here I'm going to come back to this example of support for the death penalty, and we're going to compare the numbers we can get for death penalty support in two samples. One of them is the data from our class. So this was one of the questions I asked you in the class sample, and I asked it using this very specific wording for a reason, which was, do you favor or oppose the death penalty for persons convicted of murder? And when I asked the class this, I got this distribution. A little over 53% of the class said that they oppose the death penalty for people convicted of murder, and a little over 46% said that they favor the death penalty for people convicted of murder. This exact same question has been asked to people in a representative sample of the US population many times, and it was asked most recently in 2021. And this is from a survey called the General Social Survey. And when asked of a representative population sample, we get the exact opposite set of results. So if you ask a representative sample of the US population, we can see that more people favor than oppose the death penalty, where about 56% of the US representative sample says they favor the death penalty, and little under 44% of the US representative sample opposes the death penalty. So what's going on here? Why is it that if I take a sample of students in this class versus a sample of people in the US, I'm going to get completely different results? And what's really going on is that the data analysis sample is not representative of the US population overall. So you guys are in my class not as a simple random sample of people in the US, but as a sample of college students who are interested in studying criminal justice and got stuck in a statistics class as part of that. But in many ways, you are going to be different from the overall population, and those are ways that can impact your support for the death penalty. So one of the biggest ways that the sample of students in this class differs from the US population is that you are, on average, more educated. So about 35% of people in the US generally have a bachelor's degree. Well, 100% of people in this class are going to have a bachelor's degree soon. And education is something that's related to death penalty support. And you guys also differ on other dimensions that are related to death penalty support. So compared to a data analysis class, the US population tends to be older, whiter, more conservative, and those are also things that all play into death penalty support as well. So what we would conclude if we only looked at the data analysis class is that, well, people generally oppose the death penalty more than they favor it. But we'd be wrong, because our population sample, or our sample of the US population, would show us the exact opposite, and that's because our data analysis class sample is not representative of the US population. And the characteristics of our class sample are not going to match the characteristics of the US population overall. So when considering statistics that you see out there in the world, always ask yourself, what's the sample this is taken from? If it's a representative sample, like one that you see in a political poll, for the most part, you can trust those results, because you can expect that within some margin of error, the values in that representative sample are going to match the values in the population. But if a sample is collected through other means, other than sampling that's representative, then you might have a problem. So if you have a sample that's collected through a process that's not random selection of members on a list or something similar, then you might end up with results that are wonky. And so again, we wouldn't want to use our data analysis class to try to understand trends in the US population as a whole, because our characteristics of our class are going to be different from characteristics of the wider US population in various ways. And this issue has played out before, and what I'm going to do is attempt to use some YouTube wizardry in a moment and just play this video immediately after I stop talking. But before I do that, I'll say that the differences between our sample statistics and population parameters that happen because of bad sample selection, from selecting a sample that was not actually representative, results in something we call sampling bias. So if I try to use a data analysis class sample to describe attitudes about the US population as a whole, I would have sampling bias as a problem, because my data analysis class sample is not representative of my population of interest overall. Alright, and here we go. I'm going to attempt to play this video next in the chain of videos, and then after that it'll go into the participation activity for this day.